Okay.
How many does he have?
Here's where we left off yesterday. Remember? Okay, we were looking at this function,
Yes.
right?
That's correct.
Okay, quick review. We took the derivatives. The function was, we found out that there were no critical numbers. Right? We had no critical numbers of the first or second derivative. But we did have a discontinuity in the function that we decided was a vertical asymptote. And why was x equals negative 1 a vertical asymptote? Bottom is 0, but top is not 0. Good, okay? Perfect. So we had a vertical asymptote. We've got a new technique. We know that if we have a rational function like this, if we take, we can take the limit at infinity, right, to find out if there's a horizontal asymptote. And we decided this one did have a horizontal asymptote at y equals 2. And why was that? When I take this limit of this function, why do I know that the limit at plus or minus infinity is positive 2?
Usually back on x and they cancel and the 2's left on top.
Okay, yeah, and let's take just a brief review of the 3 examples we looked at. Right, we looked at one like this. Is that the first one we did? No.
No.
There's the first one we did. Okay, we did one like that, and we got back an answer of 0. Took the limit of a rational function, and the limit was 0 as x approaches the infinities. And somebody remind us why we knew.
Because the order of the exponent on the denominator was lower or higher than the top.
Okay, good. The order of the polynomial on the bottom is higher than the top. It's a more powerful polynomial, the leading term. So it goes to infinity faster. So the bottom gets bigger, in other words, right? So we know that drives the behavior to 0, right? And then that one ended up being 2/5. Because I think maybe we already mentioned that. Because the orders of the polynomials are equal. So then we just look at the ratio of the leading coefficients. Okay, and notice on both of these too. This is kind of an important point too. We know that there's one asymptote for both tails if it's a rational function, right? In this case, that is a horizontal asymptote, isn't it? Right, y equals 0. That's just the x-axis. So we know that as we go out to either tail, this function's gonna just settle down onto the x-axis, right? And that's a horizontal asymptote. This was a horizontal asymptote that in this case was a little above the x-axis, but that's all right. Same deal, right? But once again, it's the limit as x approaches plus or minus infinity. So we get this one asymptote that serves both tails, okay? And then the third case, we had one where the top was a higher order polynomial, and that one exploded. And we had to just look, though, we wanted to know in what direction did it explode. And so we just looked at the sign of the leading term, and that tells us the direction that it's exploding. It's going infinite, but we just need to know up or down, right? Okay? And so when we use that now in our tables, that gives us some additional information. We know we have this horizontal asymptote, and so we've added some new features to our table. We get this dashed line that tells us, and -1 was an undefined function, so that told us it was a vertical asymptote, and that's handy. That divides this thing up, right? The limits at negative infinity and positive infinity, the y value was 2, so that's telling us it's a horizontal asymptote, right? All these other features, none of them are the stuff we've been talking about in the past, but they still fit on the table. And so let's just finish this guy up. What could we do here now? If we want to, really just get an idea what this thing looks like. That's pretty helpful at this point. If we wanted to do a sketch, I'll have to kind of compress this sketch a little bit here, but it looks something like this, doesn't it? We know we've got a vertical asymptote that helps us, that kind of gives us sort of an idea how our function's got to go at x equals 0. We had a horizontal asymptote.
Is it -1?
Oh, it's at 1. Whoops. Okay. So you go all that far back, did I? Like so, at 1, like I said.
-1.
Negative. Oh my gosh, are you kidding me?
Well, why? Yeah, it's usually what. When we start teaching.
All right, yeah.
That's when we're done.
Producers, gang.
Alright, so how's this? There we go, negative one.
That's much better.
Now, is that right, or did I make another mistake?
I like it.
And then we had a horizontal asymptote at y equals 2. But that still gives us some possibility. There's several things that could be happening, right? We know that it could be doing, there are no peaks or valleys, so it's pretty boring. It's either doing that over there, right? Or it's doing that, right? You see that it has to? Now, the specifics, we don't know, does it push clear into there, or is it, we don't know that, so we don't really care though. We can always throw a few points in there if we really want to know more accurately. So it's going to be a combination of 2 of those 4 pieces, but we don't know which ones. We got to figure it out. So how might we do that? Test points, okay. So test points, obviously on either side of the vertical asymptote, but now here's the next question I want you to think about. Where do we want test points for what row? I mean, a bunch of them will work, but what's kind of our rule with that? We always, as far down as we can, yeah. So if we do test points, and all we need is a sign of the second derivative, right? So if we take our second derivative and we evaluate this at 0, is it going to be positive or negative? In fact, well, okay, no, never mind. It's going to be negative there, isn't it, right? So we get negative there. If I take a value like at -2, for example, what's that going to give us? Negative on the top always. If I put -2 in for x, what's going to be the sign of the bottom? Negative, because I'm going to get a negative number to an odd power, which stays negative. Does that make sense? Negative over negative is positive.
Definitely.
And so that's telling us concavity. And that's really all we need then, isn't it? If it's positive concavity to the left of the asymptote, which of these, I'll call it top or bottom, which of those 2 pieces would apply? Has to be the top one, doesn't it? Right? It's got to adhere to both asymptotes. And this would be concave up. Right?
How did we get the negative over the negative again?
For this guy right here? Is it, all we did was evaluate the second derivative. We want the sign. We don't care about the value. We want the sign of the second derivative when x is -2.
Did you say that we have like negative over negative though?
Yeah, because if I put -2 in, look what's going to happen. I'm going to get -6. -2 plus 1 is -1 cubed.
Oh.
And if I have a negative number to an odd power, it stays negative.
Oh, and then it's positive. Okay.
Right, so the overall sign would be negative over negative, which makes it positive.
Okay.
Okay?
I was thinking 0.
Now over here we get negative, so it's got to be the bottom of the 2, right? So it looks like that. Does that make sense?
Mm-hmm.
Okay. This gives you an idea how we can still use this table even though there are no critical numbers. It's still handy. Okay. All right. One last thing I want to show you, and then I think we'll just get you to work a little bit. So what about if we have something like this? Let's try.
Big age.
Limit of, say, 3x minus 2 over the square root of 2x squared plus 1. Let's do this as x approaches positive infinity. Okay, now is that a rational function? Remember, what was the definition we said of a rational function? Remember that was the p over q? Well, what were the p and the q? What kind of things were they? Polynomials, yeah. So is that a rational function then? No, it's not. I've got a polynomial inside the radical, but it's a square root, so it's not a rational function anymore. But we can maybe treat it sort of using the same thinking. Okay? Any ideas how we could deal with this? Say it again. Okay, I mean, we could put it to the power of 1/2. And we could probably try to do some, well, I mean, we definitely could try to take some kind of a limit where we multiply by, you know, we multiply by a square root or do, but maybe we don't need to. Think about the behavior of those polynomials we were talking about. If we go back and glance at those examples that we looked at in the past, remember, all we really cared about when we're taking a limit at infinity, when we're dealing with a polynomial, is the leading term, right? Because everything else, remember, is dwarfed by the leading term. If this is an x cubed and that's merely an x squared, as x gets really big, x cubed is much, much bigger. In fact, as x goes to infinity, you know, we even said it's infinitely bigger, right? So only the leading terms really count in a polynomial, right? Now look at this example here. Even though that's not a polynomial on the bottom, the part of the function inside the radical is a polynomial, right? And so as x approaches infinity, or negative infinity, infinity in this case, doesn't it make sense that really the only part of that square root that's going to matter is the 2x squared? Okay, that makes things easier. If we can consider that only including the first term, look how much easier this is. This is equivalent to the limit of 3x over the square root of 2x squared, right? What can I do to the bottom?
Can you do the 1/2 now?
I mean, I could. I don't really need to. If I have a square root of a product, what can I do with that? For example, if I have the square root of AB, any tricks?
I'll separate it.
I can separate them, right? I could write it as the product of the square roots. So I could write this as,
Root 2 times.
yeah,
x
yeah,
squared.
exactly. I could write it as the limit of 3x over the square root of 2 times the square root of x squared. But what is, we've talked about that, what is the square root of x squared?
X.
No,
1,
not x.
0,
Say it again? No? In a sense, yeah, but that's the definition of a function. Think what this does. If I input positive 3, 3 squared is 9, square root of 9 is 3. If I input negative 3, negative 3 squared is,
What was it, like x?
square root of 9 is, so what do you know that leaves a positive? Say it again? Positive, well, it's not just positive x. Absolute value, yeah, that's the definition of an absolute value function, right? So that's the absolute value of x. Okay. So we end up with 3x over the square root of 2 times the absolute value of x, okay, as x approaches infinity. So x over the square root of x. Now, what's that going to look like? X over the, if I graph that function, let's just think about just that part for a second. If I take the function g of x equals x over the square root of x, or it turns out square root of x over x, it doesn't matter. What's that going to look like?
1.
It's going to be 1 sometimes. What is the absolute value of x equal to when x is greater than 0?
Positive.
Positive x, right? What's it equal to when x is less than 0?
Positive x. Negative x.
Negative x, right?
Wait.
Because it's got to end up being a positive answer, right? When x is negative, it's got to be the opposite of x. Because doesn't it always output a positive answer?
Yeah.
Right? Does that make sense? Okay, so then if we write this as a piecewise function, it's equal to x over x whenever x is greater than 0, but it equals x over negative x when x is less than 0, right? Well, what's x over x? That's 1, right? So, looks like that. what's x over negative x? Negative 1. So it looks like that, but x is negative.
Why does the absolute value turn negative?
It doesn't turn negative. We have it's
Wouldn't it
always
go
positive,
down?
but to ensure,
yeah.
does that make sense? To ensure that it stays stays positive, like take a number, for example. What if I plug in -3? If x is -3, this needs to output a value of positive 3,
Okay, yeah,
right?
yeah.
So I'd have to multiply the -3 by -1,
Yeah.
right?
Yeah.
To sort of cancel the negative, like you think of it. Okay, so what does that say about our example then? Here is this x over the absolute value of x. And that might seem like, wow, that's a weird logic, but that comes up a lot. The square root of, or the absolute value of x over x or vice versa is a function that you see a fair amount for some reason. It's out there. And you see it like in quantum mechanics. I mean, it's something that does show up. So what does this thing look like then? Well, it's got two different asymptotes, doesn't it? Right? If we take the limit at positive infinity, and this we are talking about positive infinity here, then that's just going to be what? 1, isn't it?
Yeah.
Right? Because x is positive there, and so we end up with infinity over infinity. I mean, no, x over x, really.
Yeah.
It's infinity over infinity. But that's 1, and so we just get the answer 3 over the square root of 2, right? If we did the very same limit to the other direction though, right, to the opposite tails, we're going to get, see what I'm saying? We get the limit of 3x over the square root of 2, so the value of x, as x approaches negative infinity. Now what's that going to be? Negative 1 times square root of 3 over 2, right?
Yeah.
So we end up with, oops, I guess that is backwards. There, like that.
Yes.
So we don't get one asymptote for this function, we get different asymptotes left and right. Okay? So let's try one more of those for
Let's see.
practice.
Let's see.
Try, just tell me, what would this one be? We did. Oh, that's a bad one. How did I do that? Okay, what's the square root of x to the 4th look like?
2 squared?
Yeah. Okay, I kind of threw a curveball at you here. Do you really even need an absolute value for that? Is x squared ever negative? No, so this one you didn't even need it for. But the point being, what I want you to be looking at, maybe that wasn't a very fair way to do it, is I want you to look at this. We have a square root of an x to the 4th, right? And so that just gives us square root of 4 is 2, and then we get, don't need the absolute value bars, right? But, just so you can see the connection, over 3x squared and then plus a bunch of minor league stuff that we don't care about. So when we take this limit, so those cancel. In this case, it's just 2/3, right? Let's do another with the square root. Try this. Limit. So what's that going to be?
Negative root of 5 over 5.
That's a positive So that would be equivalent to the limit of what on the top?
Square root of 5.
I just look at that part. Square root of 5,
Absolute value of x.
absolute value of x, right?
Yeah.
Let's see that. And the value of that when x is positive, like in this case, be 1, right? So we just know that goes to 1. And we just get square root of 5 over 5.
Now, quick question, why is, you said the top one's going towards a negative infinity, but it's just positive 2/3.
Yeah, because in this case, both of those, it doesn't matter in this case. X squared is always
Oh,
positive. That was probably a bad example to do. I probably should have just stuck with the square roots. X squares. Okay. One other. Okay, what about this guy? I'll throw one more challenge at you. What about this? What if I
I
did?
don't like challenges.
What if I did the limit of?
I have to write down challenges.
Okay, how about if we do? If we do an example.
You will be an example.
Yeah, it's good. It's limit of. Oh,
you just ruined that for me.
how's that?
Oh,
That
no, I
was on a
enjoying
roll.
this until you threw that sign in there.
Oh, no, this is good.
No, it's not.
Okay, what about that one?
Rouse is on
As
one.
x approaches infinity, the limit of sine x over x. Curious what you make of this. I'm so curious, I'm gonna give you a second to think about this. Discuss it.
I'm guessing.
So anybody have we'll brainstorm a little bit here. Anybody have any ideas to throw out?
Alright, here's a wild guess.
Okay.
So the x's are both in the same power, so
Mhm.
I'm just gonna say they cancel and you're like the sine of 1.
Sine of 1, okay.
That's what I like.
I appreciate the bravery. I'm gonna remind you of something though. This x is tied up inside a sine function, so we can't just cross it out. Yeah.
That'd be so much easier.
Oh,
It cancels.
But we got the ball rolling. So any other ideas here? Sine x over x equals, okay, now we know the limit of sine x over x as x approaches 0, right? That's one of our special limits is 1. Okay? Little different case though, so we approach infinity. What's going on?
Infinity.
What's the bottom doing?
That's what I was.
It's getting big.
Okay,
Positive.
what's the top doing?
Big. Bigger. Small.
Let's do it.
What's it doing?
0?
What's it doing? Yeah, if I look at a sine function, maybe this will help. If I look at a sine function, doesn't a sine function just do
What is that called?
oscillating behavior?
Oh, oscillating behavior.
Where it just does,
That's what it's called.
It's oscillating behaviorally.
it just does that. So does the top get big or small?
It doesn't.
What's the biggest it gets?
One.
What's the smallest it gets? Yeah,
Plus or minus one.
right. So,
Negative
So I
one,
feel
less
like it's
than or
0.
equal.
so what's this thing gonna do?
I feel it big.
Say it again?
So it makes it really small, so it's just 0.
It's 0, that's right.
Nice.
Let's go.
It is 0, because look what this does. Now, and there's this kind of thing, I think these kinds of things are sort of interesting. The top oscillates, right? It's never gonna get pinned down. And so you might think initially, well, there can't be an asymptote here, because the top is just gonna oscillate forever, right? Except, the bottom, the top also is bounded. It's bounded at 1 and negative 1. And so it never really explodes. The bottom gets infinitely big. And so regardless of the fact that the top is wavering, it's still bounded and the bottom is unbounded, right? And so really what I'm doing, and maybe a better way to think about this would be, this function would be sine x times 1 over x, right? And that's actually kind of an interesting thing to consider, because that's, when you, well, here's why. Now, a sine function looks like this, right?
Yes.
A 1 over x function looks like, an inverse function looks like that, right? And so really what the 1 over x is doing is it's just, you're multiplying this sign, which is limited at positive 1 and negative 1, by some multiplier that's either going to stretch the sine function or shrink it. Does that make sense? Would you agree that if I multiply sine x by 2, what's that do to the sine function? It just makes the amplitudes twice as high of the sine waves, right? So if I'm multiplying by 1 over x, it's not a constant. As x changes, that multiplier is going to change. But way down here, it's going to be huge. For values less than 1, the sine is going to be stretched really tall. Does that make sense? For values greater than 1, it's going to start to get shrunk. And so really all I'm doing is I'm just pinching the sine wave in between this envelope, and it's just going to do that.
That's just smaller and smaller.
Yeah. You see how that works?
Yeah.
And so it's still going to get pinched down to 0. It's just going to waver around 0, but if you go infinitely far out there, the wavers get infinitely small. Right? Does that make sense?
Wow.
Kind of interesting,
Yeah.
huh? Yeah.
Okay. Fascinating.
All right.